Okay, before we continue RDT 2.2, let's review some of the RDT final estimations that we talked about last week. And for the very first RDT 1.0, we have an assumption that the underlying protocol, the underlying layer 3, is perfectly reliable. So that in RDT 1.0, which is right here, right? We only need to forward the messages from the layer 7 protocol and create the corresponding layer 4 headers and pass the segment to layer 3. Because the underlying channel is perfectly reliable, so that the packet will goes to the receiver and will be forward by its layer 3 to layer 4 program. So layer 4 program is very the concept is very easy. It only has to extract the packet and deliver data, and that's all, because the underlying channel is perfectly reliable. But in RD 2.0, the channel is with bit errors, so packet is actually arrived at the receiver side, but we need some mechanism like checksum, like acknowledgement, to make sure the packet is delivered and the packet has no error. So we need a checksum to do such kind of check, and the check result will be goes back to the sender by using either acknowledgement or negative acknowledgement, right? But we have talked about some implementation of RDT 2.0, and we see that there is a fatal flaw, because the acknowledgement and the negative acknowledgement should be checked again at the sender side when the sender receives such kind of acknowledgement, right? So we have 2.1, and now we have 2.2. Okay, it is another version of reliable data transfer protocol, and in this 2.2, the functionality is exactly the same as 2.1, but there's one important thing we like to demonstrate, that it is possible for us to only use acknowledgement without using negative acknowledgement. So it will be more easier to design the final estimation, because we have less event, right? So think about one thing. Okay. If two, that is the sender, right? That is the receiver. And originally we sent data 1 and send egg 1, right? But what if the data right here, sorry, for example, and then we send data 0. What if we don't originally? Okay, I say originally we can send egg 0, right? However, in this case, we do not want to use for example, for example, if there's something wrong with this data 0, okay, and then for the, I should write it in this way, okay? For the receiver, okay, it originally it has to send the negative egg 0 back to the sender, right? But currently we want to eliminate using neg. So think about one thing. At this point, what else message can be sent from the receiver back to the sender, since NAC 0 cannot be used. So at this moment, in this design, okay, we send ACK1 again. Okay, we send ACK1 again, because for the receiver you can only send ACK1 or ACK0, right? But currently you cannot use negative ACK, so you cannot send negative ACK. You can only send ACK1 or ACK0. So in order to inform the sender that this D0 has something wrong, so the receiver decides to send ACK1 again, and this ACK1 is actually a duplicate ACK1 at this moment. So when sender receives such kind of ACK1, and it knows, okay, the sender expects to receive ACK0 at this moment, but it received ACK1, which is a duplicated ACK, right? So we use the duplicate ACK to replace negative acknowledgement. So right here, instead of using NAC, receiver send ACK for last packet receive OK. In this green example, that is ACK1. Okay, so receiver must explicitly include a sequence number of packet being active, so the sender know it is a duplicate ACK. So that indicates it is something wrong with the receiver. So duplicate ACK at the sender result in same action as NAC, which is retransmission. So after the sender receive the duplicated ACK1, okay, then the sender will send D0 again, and that is a retransmission. Okay, that is a retransmission. Okay, make sure you comprehend that since we cannot use NAC, so we use ACK again, but we can use the current ACK number, so we use the previous ACK number. So we have duplicate ACK, and duplicate ACK will cause the retransmission of previous packet. Okay, so for RDD 2.2, okay, that is the sender side. So follow me and let's take a look at the sender. So that is the sender's final state machine. So originally, okay, again, we have an initial state, right? So at this state, we receive message from the above layer 7 protocol, right? And assume that is the first segment, and of course, because of packet might have error, so we need to include checksum in the packet, right? So then we send the packet out. After that, we arrive the next state, which is wait for ACK0, because currently we send data 0, that is data 0, right? We send D0 to the receiver. Okay, so that is the step number 2. When we are waiting for ACK number 0, okay, and here we indeed get a packet. The packet is sent from the receiver, and there are two different situations. The first one is, although I know I get a packet from the receiver, but I cannot understand what exactly the information included in the packet because it is corrupted. Or situation 2.2-2, I actually know it is an ACK sent by the receiver, but currently I'm waiting for ACK0, but the current ACK that I receive is ACK number 1. So no matter what, these two different situations indicate that there is something wrong with the receiver. So at this moment, as a sender, we simply just retransmit the previous packet, which is data 0. So that is data 0. Retransmit. We retransmit this data 0 because receiver give the sender certain information, but we cannot know what exactly is, or it is a wrong ACK number, because currently I'm expecting ACK number 0, but I received packet ACK number 1, or it is a corrupted packet. So I simply just retransmit data number 0. Okay. So next is step number 3. Okay. If at this moment, when I'm waiting for ACK number 0 and I receive the packet is not corrupted, and it is actually ACK number 0. And then, as a sender, I goes to the next state. It should be symmetric state, right? So that is wait for call 1 from above. Right, so actually it has 4 states, but it is symmetric states, right? So as long as you can comprehend what exactly what is going on right here, step number 1, 2, 3, then the other side is just change another sequence number. Okay, so that is the sender's finite state machine. And on the other hand, right here, it is the receiver's finite state machine. Okay, so let's take a look at number 4 right here. Okay, so currently, right, there should be one state. Currently, receiver is expecting data number 1. Okay, and it receives a packet, and it is not corrupted, and indeed, it is data number 1. So event number 4, that means everything's fine, everything's okay. So after that, data number 1, okay, will be extracted from the segment and will be delivered to the layer 7 protocol. And at this moment, the receiver will reply ACK number 1 with its checksum and send the packet, right? So after that, receiver goes to next state. Currently, receiver is expecting the next packet, which is packet number 0, because we have only 2 sequence numbers. So either it is 1 or it is 0. So after I receive packet number 1, then the receiver is expecting packet number 0. So here is the problem right here. If you are expecting data number 0, and currently you have a packet, but it is either corrupted or it has a wrong sequence number, because currently we are waiting for packet 0. Sequence number is 0, right? So there must be something wrong with the sender, right? So in this case, for the receiver, it will retransmit the previous ACK, which is ACK number 1. So that the sender can after sender receives such kind of ACK number 1, which is a duplicate ACK, right? So at this moment we send the first ACK number 1, and this moment we retransmit this duplicate ACK. So when sender receives the duplicate ACK, it knows, okay, there's something wrong with the transmission, so it has to resend, right, packet with sequence 0, data sequence 0. Okay, so I think that's RDT 2.2. I think it is still not that difficult to understand the entire behavior of sender and the receiver, as long as you know that currently we don't have neck, so we simply use the previous egg to represent there's something wrong with the communication. So we use when you receive duplicate egg or duplicated packet, then you simply just do the retransmission. So the packet or the egg will be transmitted to the other side, and they will understand, okay, that there's something wrong with the communication, so we can do the recovery by using retransmission. Okay, so that is RDT 2.2, sender and receiver. Okay, and the next situation is more complex. In RDT 2.0, we assume the channel with errors. So, but the channel in RDT 2.0, they have no loss. So when the sender sends a packet, it will arrive to the receiver side, but it might corrupt it or it might be okay. But in RDT 3.0, when sender sends a packet, okay, right here, when sender sends a packet, right, this packet D1 might never arrive to the receiver because packet might not get lost. Okay. So think about one interesting thing. Okay, S is the only person who knows it sent D1, right? Receiver never knows D1 get lost in the routers, right? So if in this kind of complex environment, S sender is the only person who can design a recovery mechanism, because R receiver never knows such kind of D1 data packet, right? So in RDT 3.0, okay, so when the sender send the packet out, it should set a timer right here. So with a reasonable time, okay, we will tell you what is the reasonable time in the later class. Okay, in the reasonable time, if the sender did not get egg number 1, and then we will trigger, the timer will be triggered, and the sender will send, that is a retransmission. The sender will retransmit the packet again when the timer is triggered. Because as sender is the only person who knows it has sent D1 before, but it does not get any egg 1 within this period of time, so it retransmit D1 again. Okay, and there's another situation like this. Okay, I think it is quite easy to understand. Okay, it's in the D0, A0, D1, A1. But in this case, okay, D1 has been delivered to the receiver, and A1 get lost when they send it back to the sender, right? But every time when the sender send a packet, it should set up a timer. Okay, and again, no matter D1 get lost in the router or A1 get lost in the router, if S does not get the response, which is A1, and eventually the timer timeouts, and then sender will retransmit the packet that it will retransmit the packet that the response is missing. Okay, so that is very simple and elegant design to use a timer to guess, okay, to make a guess that there's something wrong with the communication channel. So right here we have a new assumption that underlying the channel can also lose packet, okay, no matter if it's a data packet or it is an ACK packet. In previously, we have different mechanisms like checksum to deal with the error problems. We have the acknowledgement to make sure the checksum, the result of the checksum is sent back to the sender, right? But since we have negative acknowledgement or acknowledgement, we need to retransmit the packet, so we need a sequence number. But they are helpful, but they're not enough to deal with the channel with loss. Okay, so we have a timer, new timer design right here. So the sender waits reasonable amount of time for ACK. Okay, if no ACK received within this period of time, and we do retransmission, right? If packet or ACK just delay, not lost. Okay, think about one thing right here. Think about one interesting thing is that what if the ACK late A1, okay? What if the ACK 1 is simply just delayed by the routers, but we have a timer right here, so the timer is triggered. So the new D1, which is a retransmit, the red D1, the red retransmit D1 has been sent, but after that we get the blue late acknowledge 1. Okay, it is possible. Okay, because we cannot predict the delay of the network, so it is possible. So after that, the sender cannot know. Okay, after that, there should be an after receiver get D1, right? The receiver will send A1 again, but actually the sender does not know it is the previous late A1 or it is a new A1 from the receiver. The sender cannot tell, right? But it is okay because no matter which A1 the sender gets, the sender knows A1 is correctly arrived at the receiver side, right? So no matter which blue A1 that the user, the sender gets, it is okay. But sometimes the sender might get duplicate ACK, right? For example, right here we have a late A1 and we have the retransmitted A1, right? So sometimes the sender will get the unexpected acknowledge packet with unexpected number, but it is okay. It is okay. We simply just ignore those duplicate ACK at the sender, which is good enough. Okay. So right here, we have the RTV 3.0, which is sender's finite state machine. So again, let's try here. We have a message right here, right? So we get the data and we send the D0. And we have a checksum right here. And we simply just send the packet out. But you have to notice that because we need a timer to deal with the loss problem. So every time when you send a data packet out, you have to set a timer for this data packet. For example, that is T0. We just simply write T0 right here, okay? And then we goes to this part. Right? Currently, the sender is waiting for ACK number 0, right? However, right here, now timeout is a new event to this finite state machine. So if T0 times timeout, okay, we will get such kind of event. And then we know, okay, there's something wrong because we never receive A0, acknowledge number 0, right? We wait until timeout. So at this moment, we know there's something wrong with the previous data, which is D0, right? So currently, we simply just retransmit D0 right here. And don't forget that since it is a retransmission, we still need to set up a timer for this retransmitted D0, which is the purple one. Right? It's quite easier to understand. And then right here, we have step number 3. Okay? If we receive packet, which should be an ACK packet from the receiver, right? And 3-1, 3-2, okay? The first situation is that we cannot understand what exactly the packet is, so it is corrupted. Or it is an ACK, but currently we are waiting for ACK0, right? Because we send D0 to the receiver. But currently we get ACK number 1. That means it is a delayed ACK or it is a duplicate ACK. So, but interesting is that we don't do anything right here. In previously, when we receive a corrupt packet or receive a packet which is not the sequence number is not what we expect, we do retransmission, right, as state number 3. But currently we have timer. So in RDT 3.0, all the retransmission only depends on the timeout. So even if you receive a corrupt packet, if you receive a ACK without correct number, we simply just do nothing as step number 3. And we will wait until the timeout. Or step number 4, we receive the packet and the packet is not corrupted and it has expected sequence number. And then we will stop the timer, set up right here or set up right here. And then we continue to the next state, waiting for call from above using sequence number 1. Okay, so in RDT 3.0, currently we don't do any retransmission based on the acknowledged number or the corrupt packet. We only retransmit the packet depend on timers. Okay, that is a little bit different. Okay, and again we have a small we have another event right here. Because we send a duplicate ACK, we have duplicate data and we have a late acknowledgement number. So sometimes we will receive packet from the receiver when we are already leave sequence number 0. Currently we are on round number 1, right? We are waiting for call from above and waiting for data number 1. All things about data 0 and ACK 0 are done, right? But sometimes we will receive packet, acknowledged packet from the receiver. For example, right here, this one, right? Because of the late ACK and this such kind of duplicate ACK. Sometimes we will receive packet at this moment, but we simply just ignore these things because we have already received the correct ACK once. So if we have 2 acknowledgements, okay, we should simply just ignore the second one. So that is the RDT 3.0 sender. So we can see that again, it is symmetric. So the right hand side, right up side, that is the round number 1, and the left bottom side, that is the round number 1, because they use the sequence number 1. Okay. And again, you can simply just Google RDT 3.0 receiver, because our textbook does not provide RDT 3.0 receivers finite state machine, so you can check it out on Google. Okay, some people is kindly share RDT 3.0 receiver. Okay, so that is RDT 3.0. So let's take a look at some example right here. So figure A, so that is quite normal. We send packet 0, we have ACK 0, packet 1, ACK 1, packet 0, ACK. We just keep using the different sequence number. And of course, we can use sequence number 2, which is okay. But since we don't want to maintain too many states, so we simply just reuse 0, sequence number 0 right here, because after, you can see that at this yellow point, okay, when the receiver send the ACK 1 and the sender receive the ACK 1, they both know packet, I mean round 1, okay, round 1 is done, and round 0 is done already. Okay, so after that, we know round 0 is already done, and round packet 1 is done right here. So we can reuse sequence number 0 after round 1. Okay, at the right hand side, okay, that is one of the situation that we mentioned. If the packet 1 get lost, okay, there should be a timer right here when you send the packet out, right? So when the packet time out, we retransmit the packet, and again, the receiver will receive the packet number 1 and send the ACK again, and so on and so forth. So here again, the left hand side is the we lost the packet, sorry, we lost the ACK number 1. But again, when the sender send the packet 1 out, it set up a timer right here. So as long as the ACK number 1 get lost, so timer will trigger somewhere right here, and the receiver will receive the duplicated packet number 1, but the receiver will send the ACK again. So on and so forth, so on and so forth. And at the right hand side is the delay ACK. Okay, as we mentioned before, when we send the packet out, if the timer is too small, too short, okay, the ACK, the sender will send out the packet first, and the late ACK will be received. But it is okay, because when you take a look at the center side, okay, timeout send ACK and send packet 1, get ACK 1, send packet 0, get ACK 1, ignore it, okay, send ACK 0, which is okay, send packet 1. So if you simply just take a look at one side, the sender, when it receives ACK 0, then send packet 1. When it receives packet 1, send packet 0. When it sends duplicate ACK, simply just ignore it. The rule is quite simple at the center side. And again, at the receiver side, when it receives packet 0 and send packet, send ACK 1, send get packet 1, send ACK 1, send duplicate packet, send duplicate corresponding ACK. So the rule is still very simple. Okay, simply just follow it. Okay, so let's take a look at okay, we stop it right here because the next one is another topic. So that is RDT 3.0. Okay, we simply just stop right here. We'll continue later.